This is going to be geared towards beginners, entry level. The idea is to hope that we can get everyone in the company to be able to speak to hydraulics and help you in whatever field you're in. So Glen's been doing it his whole life. I don't think there's a better instructor that we could have. So Glen, it's all yours.
Okay, thanks, Chris. So as I was thinking about what to start with and how to lay it out, I figured we would just splash into this. Again, assuming this is just a very simple, basic course to start getting people think about hydraulics and the concepts. So it was very easy to say, well, let's just understand what the word hydraulics means. And the interesting thing, and we have half of that word in the name of our company, Airline Hydraulics. Just to introduce myself a little bit more, I look at some of the names on there, and half the people I don't even know. I have been at Airline for 22 years. All total, probably in my career, I started dabbling in the hydraulics in the 70s, late 70s. So that's 45 plus years of all different kind of experience. I've actually been in heavy industry. I've rotated turns. I've been in field service. I've been involved with big installations, design, engineering. So you name it, I have a good feel for all the different type of concepts as it relates to hydraulics. I'm going to share my screen here. So as I had mentioned, that's what we're going to really look at, is what the term or what the word hydraulics means. Okay, and that's what this whole session will be on today. I think some of the younger people that are new to the company might wonder what hydraulics is, what the term means. I wouldn't say that everybody understands it, but really it's the hidden application of physics that really play a huge role in so many different machines, so many different things going on in the world ahead of us and around us that it's everywhere. You may not even know it's there. So much of hydraulics is hidden behind plates, inside of stuff, and you don't see it, but it's working away there. So it's really an application of physics that we use day in, day out to do a lot of work throughout industries. You name it, you're going to see hydraulics around. It's quite fascinating the places that you find it to be after you start looking for it. It's there. Probably, I would venture to say 99%, if not all, of airline employees own a hydraulic system or operate a hydraulic system. You might have not thought about that before, but again, it's there. You own one. You're using it day in and day out in your life. And that system is involved in your car, your vehicle, your truck, whatever you're using to go to and from work. The hydraulic principles are right there, right in your vehicle. So again, if you're leasing a vehicle, you own a vehicle, whatever, you own a truck, you'll have these systems in your truck, your car, whatever. The first hydraulic system that you have is your brakes. It's really a true fundamental hydraulic system. It takes the force of you putting the pedal on, your foot on the pedal, creating a force that moves a piston in the master cylinder, which applies a pressure to the fluid, brake fluid, and those lines transmit the brake fluid and the pressure down through each wheel to each one of your four wheels, which have either disc or drum brakes on, and within those brakes are little cylinders that push out due to the pressure being applied to them. And those pads on the disc or on the rotors will create a friction that slows your car down or stops your car. That's a hydraulic application right there. So you are the pump, if you will, or you are the force, which is in your leg. You push down on it, and through the brakes, the pressure is transmitted through all the lines down to the brake system, and you're able to stop or slow down your car. That's hydraulics. We'll dig into that a little bit more, but it's there, right? Moving to the second item that you own or operate, your transmission. There are vehicles out there that don't have an automatic transmission, but a lot of people will have an automatic transmission within their car. That transmission is basically the device that transfers the horsepower from your engine to all four wheels. Within that transmission, There's a pump, there's transmission fluid, there's valving, and there's hydraulic clutches. There's a hydraulic system within the automatic transmission. Quite fascinating device if you ever look at it in detail. And if you see a schematic on the transmission, it's quite detailed. But still, it's a fundamental hydraulic system that is manipulating a lot of horsepower and transferring that horsepower to your 2 wheels or 4 wheels, depending on what kind of vehicle you have. Again, that's hydraulics. The next item you probably have on your vehicle is power steering. There are cars that do not have power steering, but most of them that I would say you're using today would have. Although I have classics here that have some manual steering, and you know right away that it's manual steering. It's very hard to turn, especially if you're sitting still. The power steering basically is part of the system, and as you turn your steering wheel left or right to turn the front wheels left or right, there is a pump in the engine compartment that has fluid in, and that is pumping it. And as you turn your wheel, it moves the steering column, which changes the valving within the steering and allows pressure to come down from the power steering reservoir to drive your steering left or right. And there again, you've got a hydraulic system within the power steering. Now, there are cars with electrical steering or electrical assist, but I would venture to say 8 out of 10 cars probably have power hydraulic systems on them. So probably already people on this team's meeting mightn't have realized that they probably own 3 hydraulic systems, and hopefully over the life of the car that you maintain some of these systems a little bit, especially the automatic transmission. They do have filters in them, especially the transmissions. You can change the filter, you can change the fluid, and what have you, much like you would do in a system in industry or mobile. But just goes to show you, everybody has hydraulic systems in their life right in front of you. So the word itself, hydraulics, is derived from the Greek word for water. We're not going to talk too much about water, but I figure I'd touch on it here because it is part of hydraulics, if you will, when you're talking about the introduction of hydraulics. I have 2 illustrations there. One basically just shows you the old time flour mills or grinding mills that were put alongside the rivers or in the creeks using the water energy, the kinetic energy or the momentum of the water, as you see in the mill, or if you look at the right-hand side, a hydroelectric power plant, the water comes down out of the dam area, flows through a chamber or opening there in the dam, down through the turbine, out of the turbine to the river below. Again, kinetic energy or the momentum of water. One turn in the grinder inside the mill, taking your corn and you grind it into flour, if you will, back in the day. Not too much that being done today, but it was how they did it years ago. And again, there are still electro-hydraulic power plants out there that take that energy from the water that turns the turbine around. It generates electricity to be used for residential or industrial use. Again, this is, using water itself. We're not going to talk about this, but it was just a good starting point to talk about the hydraulics. So we have to make a distinction between devices that uses the impact or momentum of a moving liquid such as water and those that are operated by pushing on a confined fluid, such as I was talking about your brakes. When you push on that brake pedal, you're pushing on a confined fluid that generates a pressure that now is transmitted down to your brakes. So we got to talk differently here, and we're really going to concentrate on that second sentence I have underlined there, the operation by pushing on a confined fluid by pressure, more so than we're going to talk about the other subject, which is the one would be the term that we're just going to touch on and then move away from, is the hydraulic device which impacts or kinetic energy on liquid to transmit power is called hydrodynamic device. That's what the past slide shows. Okay, the power plant is a good example of that. If the device is operated by a force, such as your foot on the brake pedal applied to a confined liquid, beyond the brake pedal, there's a chamber that the fluid's being compressed. That's called a hydrostatic device. Okay, pressure being applied on which generates a force, distributed over the area, exposed as force per unit area. That's what we're going to be. This is really what we're going to be focusing on, is the hydrostatic device. Okay, that's what we would really be driving into and trying to understand more in these future sessions coming up. The statement, pressure being the force applied, which again, going back to the brake system, your foot, right, pushing on the brakes, distributes over the area exposed as force per unit area, brings up a very important thing that we'll talk about mostly here, is Pascal's law. Pascal was a French scientist who come up with this concept, or this relationship, and it's really what hydraulics is all about. It's really the basis of hydraulics. There's a lot of different areas you can get into, but understanding this is how hydraulic operates, and this would be important to grasp today. If you get anything out of this class, the next several slides will touch on this more detail, but it's the foundation of hydraulics. The pressure applied on a confined fluid, okay, is transmitted, transferred, undiminished in all directions, acts with equal force on equal areas and at right angles to them, which is really how your braking system works. When you push on the brake pedal, you're pushing on that confined force that now is pushed out into the brake lines, all the ways down to each wheel, into the braking chambers, into the cylinders, thus pushing out the pads on the brakes, creating friction to stop or slow down your vehicle. That is Pascal's law in its truest sense. And we'll see some better illustrations of that as we go along here. I got a pretty good 5-minute PowerPoint, 5-minute YouTube video we'll look at, and you'll see that braking system a little bit more automated. Here, if you look on the left-hand side, I'm showing a container, and in that container is some kind of fluid. It could be water, it could be oil, but it's a fluid that we will consider non-compressible, right, for these terms here. You can see on the top there that you're pushing with 10 pounds of force by using your finger on that cork. That cork has an area of 1 square inch, right? So as you push down, and thinking about Pascal's law, saying that force now is going to be transmitted and undiminished in all areas, all directions, that same force that's on the end of that cork that's being generated by you pushing down that cork into the container now acts on every surface area inside that container. Okay, so within the container, based on some formulas we'll see here, simple relationships, 10 pounds on that one force creates 10 psi per square inch inside that chamber. Okay, and since the fluid is not compressible, for our terms here, in the higher end hydraulics, it is compressible, but in conventional hydraulics, it is not. That pressure is exhibited in all directions on the side of that container. On the very bottom of that container, it's showing a surface area of 20 square inches, so 10 pounds psi per each unit of the 20 inches squared gives us 200 pounds of force that's being applied on the bottom. So I've said a lot there, and there's a lot in the illustration, but the real key of hydraulics, the workhorse of hydraulics, the power that you get out of hydraulics is really a relationship. If you're looking at the top there, 10 pounds of force at the top now has created 200 pounds of force on the bottom. So it's a quite a significant ratio there of multiplication of force. And that is the true sense of hydraulics. That's the power you get out of using hydraulics. This is the relationship of Pascal's law, force, pressure, and area. We got the little cheater triangle on the left-hand side of the screen there. And it shows you that force is units of pounds. Pressure is in units of pounds per square inch, and then area is in units of square inches. So we can solve for any one of those three variables in the triangle there by looking at the simple equations in the bottom right there, being force is equal to pressure times area. This is really used so much in hydraulics. If you look at pumps, if you look at compensators, if you look at valves, you look at sophisticated valves, you look at prop valves, relief valves, there's a lot of pressures acting on areas within those devices, creating force balances or force differences between springs and hydraulic pressure that really make up that simple relationship of force is equal pressure times area. The second one down is pressure. So solving for pressure, you would take the force that you know and divide it by the area. And then the third one being area, you take the force and divide it by pressure. Okay. Very simple equations there, very simple relationships, but this is what you would start working with if you're starting to work with design and hydraulics. So going back to the filled chamber of fluid here, we call this water, we could call it oil again. By using Pascal's law and the relationship of force, pressure, and area, we can find out what the pressure is inside of that vessel. If we know the 10 inches pushing a force pushing down on the top of that cork, the cork is 1 square inch. Okay, so pressure is force times area. You can see that on the left-hand side there. I have P is equal to 10 pounds. Okay, divided by 1 square inch. Okay, so pressure that you're exerting in there due to the 10 pounds of force is 10 psi per square inch. So looking at the bottom of that container now, on the left-hand side, we find out what the force is being applied to the bottom of that container. Using that simple relationship as force is equal to pressure times area, we have force is equal to 10 psi, pounds per square inch, times 20 square inches of area. And the force in the bottom of that container is 200 pounds. So again, force at the top of the container is 10 pounds. Using Pascal's law, you push down real hard on that 10 pounds is transmitted throughout the fluid, undiminished. And then on the bottom there, since you have a surface area of 20 square inches, you have created now 200 pounds of force. 10 pounds at the top, 200 pounds on the bottom. That's quite a bit of increase in force. That's, again, a true principle of hydraulics. Kick this video here. Hopefully it goes.
Hey, Glenn, remember earlier when we were talking about maybe some hiccups doing this virtually? I think we found one.
Hiccups, yeah.
Yeah.
You can see the example, even though you're not getting the audio through, but you can see the example of the Pascal's law being utilized to lift this car up. And here again, they're showing Pascal's principle by using a balloon. As you squeeze the balloon, you'll see the pressure is moved throughout the balloon equally. And it's showing the car being lifted by the hydraulic jack, which again is Pascal's principle. This is a jack being applied to the car to lift the car up. And that's hydraulics right there. That's
So Glenn, the little piston has to go a lot further than the car moves.
what's that?
The little piston had to go a lot further than the car was raised.
Yes, yes. And I get into that a little bit, Rob, with the next couple of slides. But there's a good illustration of a brake system where up in this area here, you would apply the force to the brake by using your foot. That's going to push this piston here, which is going to push the oil on down the line. Again, Pascal's law, right? You're pushing fluid under pressure and it transmits down here and goes into the cylinder chamber and pushes these pads against this rotor, creates friction to stop your car. So it was a good illustration of the braking system. This is showing your, when you're building a home, you're using mobile hydraulics here, hydraulics all over. They're showing you where the hoses transmit, again, the fluid under pressure to the cylinders. They're actually showing you here where Pascal law even applies to your tube of toothpaste. So if you push on it, it pushes the toothpaste out the end. That's the Pascal's law. That's basic hydraulics. Going back to Pascal's law, there was a British engineer back in the 18th century, Joseph Braun, who applied his law, Pascal's discovery, in developing the first hydraulic press. And I think he got a patent for that press in around the 1890s time frame. He decided if a small force would act on a small area would create a proportional larger force on a large area. The only limit to the force a machine can exert is the area to which the pressure is applied. Okay, other than the fact that the bigger you get with some of this equipment, the more strength you need in the materials that you're building the stuff out of to contain the force and pressure generated by the hydraulics. This is a very good example of the press that he designed or developed back in the 18th century, and this pertains to what you're saying, Rob, as we work into this. But you can see where you apply 10 pounds of force on the left-hand side. Okay, that force now is pushed down on the contained fluid, which is not compressible in the red. And again, remember, that's transmitted undiminished in all directions. So it's transmitted all the ways over to the right-hand side of the actuator there, the ram. That pushes on that surface area, which is bigger, but it is able to hold up a 100-pound load. So 10 pounds of force on the left-hand side is able to hold up the 100-pound load on the right-hand side. That's hydraulics, and again, that's application of Pascal's principle right there. But one of the things you need to remember when you look at that, you got one small surface when we were on that other slide and the large surface. So something's got to give there, even though we're multiplying in force. Fundamental law of physics states that energy can neither be created nor destroyed, correct? So the multiplication of force in the press is not a matter of getting something for nothing. So yeah, although 10 pounds holds up a 100-pound force, but we're sacrificing something. So as we see in the next slide, the large piston is moved only by the liquid displaced by the small piston, making the distance each piston moves inversely proportional to its area. The key thing to remember here is what is gained in force must be sacrificed in distance. So looking at the next slide, we're moving the left-hand side of the illustration down 10 inches with 10 pounds of force. although the left-hand side, the right-hand side's only moved up 1 inch, but we're still able to move 100 pounds up in the air. That's the trade-off. That's what you lose, but what you gain is what I have at the bottom there is what hydraulics is all about, that multiplication of force, which is the workhorse in energy that you can get out of hydraulics in general by this concept right here. Here you see a huge press. This is, I believe, a press over in France. It's 65,000 ton press, which is 130 million pounds of force that press is able to generate. All through this concept of Pascal's law and the simple thing of hydraulics of putting pressure on an area. So within that press, you can't see them all, but there's multiple cylinders. 2 are facing us right here in the center, but there's 2 behind there. So those 4 cylinders together are generating 65,000 tons of force in that press. Some of the applications I've been involved with, and I'll comment on some of them, that have hydraulics, and again, use this day in and day out through all these applications, applies Pascal's law, and the force multiplication is, these are the kind of applications you can run into, but just not limited to these here. Aerospace, as you know, it's used, hydraulics are used all through aerospace, planes, jet fighters, jets, you name it, there's hydraulics. Automotive, as we've seen with the 3 applications I told you about, the hydraulics on your vehicles, brakes, power steering, automatic transmission, boats and ships, there's hydraulics all over them. Construction equipment, we see the construction equipment every day on the, on the highways, building homes, buildings, whatever. Hydraulics again, cranes, a lot of hydraulics and cranes. Electric power generation, whether it be hydropower, they use gates and different things in them. They'll have hydraulic systems. Gas-fired power plants, nuclear power plants, and also even still coal, even though coal's starting to go by the wayside. And those power plants, a lot of them have actuators that are used to control the steam. So our actuators that we build at Airline connect to the valves that control and regulate the steam that turns the big turbines that generate electricity. So we do a lot of work with that kind of stuff. Entertainment, there's hydraulics. There's hydraulics in amusement parks, different type of things used in entertainment. The Coast Guard icebreakers or ice cutters, which was a neat application. They physically break the ice where they're going up into the Arctic or Antarctic, and the ice is real thick. They'll use these Coast Guard icebreakers, and what they basically had, at least the ones I worked on, had 3 20,000 horsepower each Cat engines, and those engines drove a big drive shaft, and those three drive shafts were out the back of the ship, and they were turning a big impeller. On those impellers were blades that went back and forth in reference to degrees. So you had plus or minus 27 degrees on the blades. And based on what direction the blades tilted is how you're driving the ship, right? So if you go a negative 25 degrees, you're driving it one way. If you go a negative 25 or a positive 25 degrees, you're driving it the other way. Those blades going back and forth were driven by hydraulics. The hydraulics went down the center of the drive shafts out to the blades, and the force of hydraulics was able to drive that ship up and back, and they'll go drive up, ram into the ice, back up, ram into the ice. So a very doable thing with hydraulics that you couldn't use any other type of medium to do. Locks and dams, hydraulics that are logging and wood processing equipment. Military, there's hydraulics all through the military. And again, basic hydraulics used in the force times pressure and area. Mobile equipment, It's used everywhere, all kind of mobile equipment. The powder metal industry, they basically will fill a die with powdered metal, much like sand, and it's in the shape of a gear or a part that they want to make, and they'll bring hydraulic force down on that powdered metal and compress it at a very high tonnage. And when you're done with that, you get a metal gear or a part that's used in automotive or building tractors, what have you. Again, hydraulics at play. Got hydraulics and natural, extraction and processing of, raw materials like oil, gas, what have you, getting it out of the ground, things like that there. Hydraulics and snow removal, hydraulics and steel industry, a lot of hydraulics in the steel industry, a lot of forging that goes on, a lot of reduction in steel, and you can only do that with hydraulic force. The other interesting one was that I worked on was treadmills. And you might say, what could you use? How could you use hydraulics on treadmills? But these treadmills were built for racing horses. And they would put the horse onto the treadmill, had a hydrostatic transmission driving the treadmill that the horse was on, and then they would elevate the treadmill by hydraulics also. But here this racing horse is running on his treadmill, I guess, to keep him in condition. The other one I worked on like that was a treadmill that was inside of a big containment, if you will, like a big bathtub, and they would move the horse in there. Horse would get on a treadmill, they would fill the bathtub or this container with water, and the horse would run inside his treadmill underwater, and so interesting application of hydraulics. Tugboats, barges, waste management, where you're compressing garbage. You see many places where they're using hydraulics above and below, ground mining. So it all goes back to Pascal's law, and that application is what hydraulics is all about. But this just shows you some of the some of the applications, but it's not just limited to these applications. So if we recap what hydraulics is, which is really what we're shooting for today, it's Pascal's law, okay? So pressure applied on a confined fluid is transmitted undiminished in all directions, acts with equal force on equal areas and at right angles to them. And there's the relationship where pressure is equal to force divided by area, okay? And your area is force divided by pressure, and force that you generate out of this equipment, generate out of hydraulics, is the pressure you develop times the area you're acting on. That gives you the force. That's hydraulics right there. So the key point to remember is that hydraulics is a force multiplier, but what you gain in force, you're going to lose in distance. So there is a sacrifice there, but hydraulics is everywhere, and it's a powerful means of power transmission. So this is really a starting point to dab people into hydraulics. Sorry about the YouTube video. It worked yesterday, but didn't work today. I don't know. Anybody have any questions or comments or?
Good
Thanks,
job,
Glenn.
Glenn.
We'll see
Good to
everybody in
see
2
you.
weeks.
Okay, thank you.